Continuing on Physical Chemistry Chapter 2, we're beginning Section 4 now. We're going to talk about the first law of thermodynamics. Now, capital U is internal energy. It's the same thing as capital E for energy with a subscript internal. Now, there are going to be different types of energy that's part of internal energy. Well, first of all, there's molecular translational energy. This mostly applies to gases. When you have a gas, the molecules are all moving around. This energy is part of the internal energy of the system. There's also molecular rotational energy, depending on the type of molecules you have. There can also be molecular vibrational energy. Again, this depends on the type of molecules you have. And vibrational energy, there's types of vibrations, such as scissoring, rocking, flapping, etc. There can also be electronic energy. There can also be the rest mass energy of the electrons in the nuclei. For example, you have the rest mass times the speed of light of each proton, neutron, electron, etc. Remember, c is the speed of light, so mc squared. There's also the potential energy of interaction between molecules due to intermolecular forces, especially if you have polar molecules or hydrogen bonding, anything like that. So everything you learn in chemistry still applies. All those different energy add up to what we call internal energy of the system. So the total energy of the system is going to be the kinetic energy of the system plus the potential energy of the system. Remember, capital V in this context means potential energy plus the internal energy. So again, capital E subscript total is total energy. So K is kinetic energy, V in this context is potential energy, and then E internal is internal energy, which is the same as U, capital U. Now, K and V, the kinetic energy and potential energy, those are the macroscopic properties of the system that you can see moving around. U, the internal energy, this is microscopic. Now, of course, all these energies, energy is always extensive. It depends on mass. Now, let's just assume, though, that we have a system that is rest. So the kinetic energy is equal to 0. And let's assume that we have no external fields, such as gravity present, or the spring force, or whatever. Then the potential energy is 0. Well, then the internal energy is pretty much all the energy. So the change in energy is equal to the sum total of how it changed. Heat, Q for heat, is one type of energy transfer, and W, work, that's another type of energy transfer. So this is postulated. This postulates that the change in the energy of the system is just the sum of how you changed it. So this is a mathematical statement of the first law. Now remember, though, this only applies for closed system, and it's only true because we assume that the kinetic energy is equal to 0 and the potential energy is equal to 0. Now, if we want to change the energy of the system, one, we can let it absorb heat, which means that Q is less than 0. Or we can do work on the system, which means that W is greater than 0. Or we can let heat escape, which means Q is less than 0. Or we can let the system do work, which means the work is less than 0. Now remember, though, that the change in energy of the system plus the change in the energy of the surroundings is equal to 0 due to the conservation of energy. Now we're using SYS for system and SURR for surroundings. These are subscripts to define what type of energy we're talking about. Now if we have an infinitesimal change, then the change in the change in internal energy is equal to the differential, the change in the heat, plus the change in the work. Well, the heat and the work. Now remember, U is a state function. We're going to talk about state functions later on, but examples are temperature, pressure, and capital V for volume. So the change in the internal energy, because it's a state function, is just the final internal energy minus the initial internal energy, which means that it's not path dependent. State functions are path independent, or should I say that changes in state functions are path independent. Now, for comparison, Q, the heat transfer, is not a state function, and W, the work, is not a state function. So Q and W, those are both path dependent. I showed you earlier when we were integrating pressure volume work that, yes, it definitely made a difference. A line through a differential means a path dependent. Usually we won't bother to do this, but sometimes we will. So if you just draw the dq and put a line through the d, that's emphasizing that it's path dependent. Same with if you write dW, you write a line through the D. That's emphasizing that it's path dependent. But you don't really have to. That's just a courtesy for people who are still learning. So let's say that we have two internal energies here. Internal energy 1, internal energy 2. And there's a path here that sort of zigzags up this way and that way. I didn't even define the x-axis. Maybe it's pressure. It doesn't really matter. But it somehow it gets from here to there. Or maybe it just takes the time and goes around this way. Or maybe it does something cool, like, nice and organized motion. Either way, the change in the internal energy is the same because it's got the same final state and the same initial state. Now, a cyclic process is exactly what you think. It goes around in circles. This is our initial state. You do something, you come back to where you were. Now, we drew it as a circle. It could really be any shape. As long as you come back to where you started, it is a cyclic process. Now, what that means is the initial state of the system is equal to the final state of the system. That means our change in the internal energy is equal to 0, because internal energy is a state function. In fact, any state function, the initial and final state is going to be the same for any state function. But based on this graph, we have no idea what Q and W are, because they're not state functions. They might both be equal to 0, they could be 42, or whatever, who knows. So like I already said, internal energy, temperature, pressure, volume, those are all state functions. Now, U, of course, it's energy. Internal energy is an extensive property. Since it's energy, we measure it in joules. Joules is the SI unit for energy. And 1 calorie is defined as 4.184 joules. Now, we can make it intensive by dividing by the size. The most common way to do that is dividing by the number of moles. So if you take the internal energy divided by the number of moles, you get molar internal energy. So we say capital U subscript lowercase m is molar energy, or molar internal energy, actually. And of course, since we divided extensive by extensive, we made an intensive property. So the molar energy is an intensive property. That's all we're doing for Chapter 2, Section 4. Now, starting Chapter 2, Section 5, we've got another state function, capital H. In this context, capital H is enthalpy, not hydrogen. H is another state function. We are defining H as U plus P times V. U, remember, we defined as internal energy, capital P is pressure, capital V in this context is volume. So U is internal energy, it's got units of energy. PV, pressure times volume, we also showed before how that has units of energy. Now remember R, the gas constant, it's equal to 0.08206 liter atmospheres per mole Kelvin, or 8.314 joules per mole Kelvin, or 8.314 Pascal meters cubed per mole Kelvin. Now, to do calculations, we kind of have to know how is our what kind of process do we have? How is our system changing? One possibility is that we keep it under constant pressure. So we can say that the pressure at state 2 is equal to the pressure at state 1 and just call it P. These are capital P's for pressure. Now remember, the change in internal energy is going to be equal to Q plus W. Now remember, that's true because we're assuming from now on until further notice that K and V are both equal to 0. V meaning potential energy and K meaning kinetic energy. Now we're going to be just lazy and write Q equals Q subscript P since we're at constant pressure here. The subscript P means constant pressure and Q is heat. Now remember, work, we're talking about a pressure volume process. So work is defined as minus the integral from volume 1 to volume 2 of pressure times the differential of volume. So we're going to get U2 minus U1 is equal to Q plus W, which is equal to QP minus P, pressure is constant, so we pulled that out of the integral, times the integral from volume 1 to volume 2 of dV. That's easy. It's just V2 minus V1. So we have QP minus P times V2 minus V1. So that gives us QP is equal to U2 minus U1 plus P times final volume minus initial volume. That gives us internal energy of state 2. See how we got we're going to get all the state 2 and state 1 together. So we get the internal energy of state 2 plus the pressure times the volume of state 2 minus the internal energy of state 1 plus the pressure times the volume of state 1. Remember, we defined H equals U plus PV, so we get the enthalpy of state 2 minus the enthalpy of state 1. So QP is just the change in enthalpy. So this is very important. We put a box around it to emphasize it. The heat flow at constant pressure is equal to the change in enthalpy. But that's only true for an isobaric process. Obviously, we're talking about a closed system. If we have an open system, we can't even define the work anyway. And then remember, we did this work using pressure volume work only. If there was some other sort of work, then we'd have to throw the math in for that too. Now, what's interesting for now, at least in thermodynamics, later on we might, but we can't actually measure absolute values for enthalpy or, what the heck is this? Internal energy. But we can measure changes in internal energy and changes in enthalpy. So we have the change in enthalpy is equal to the change in internal energy plus the change in the pressure volume. Now this is true for any process, well, given the restrictions above. So the change in PV, the pressure volume, is equal to P2V2 minus P1V1. Remember, this is state 2, state 1. So the change in enthalpy is going to be equal to the change in internal energy plus pressure times the change in volume for only a constant pressure process, because we simplified it here. So and then, of course, if you divide by N, you can get an intensive version and say, okay, the change in the molar enthalpy is equal to the change in molar internal energy plus pressure times the change in molar internal energy. So just like up there, that obviously means constant pressure too. Okay, so now we're done talking about constant pressure processes for now. What if you keep the volume constant? Now remember, we showed before, if the only work you have is pressure volume work, then the differential of work is equal to minus the pressure times the differential of volume. Now since we're keeping volume constant, the differential of volume is equal to 0. And 0 times anything is 0, which means the differential of work is 0. Therefore, the work is equal to 0, because obviously if you're going to integrate 0, you're going to get 0. So the change in internal energy is equal to Q plus W, but W is 0. So the change in internal energy is just the heat at constant volume. Subscript capital V means volume, constant volume. So the change in enthalpy is going to be equal to the change in internal energy plus pressure times change in volume. That was constant pressure. But change in internal energy is going to be greater than P delta V. Because, well, it depends on, the heat flow and so on. Now remember though, pressure times change in volume is going to be small for liquids and solids, because gases, they can be compressed and expanded pretty easily. Liquids and solids, they can kind of be compressed and expanded, but not a whole lot. They're a lot harder to do. So delta V will be tiny. So for liquids and solids, we're going to just say, okay, delta V is roughly equal to 0. So the change in enthalpy for solids and liquids is going to be roughly equal to the change in internal energy. Okay, that's it for Chapter 2, Section 5.